Okay, today we're gonna speak about generalizations of Meyer Vittori sequence. That's kind of the first step towards exact, spectral sequences. Okay, somehow it disappeared. Why? Wait. Where is it? Yeah, okay, I'm here back. Well, the idea is to make a first step towards spectral sequences. Basically, spectral sequences, that's how to work with B complexes. It's when you have like many groups, like in two directions. And you compute cohomology of like B complexes. And to do that, first we're going to write Meyer Vittori sequence as a certain B complex and study it. So first of all, we want to reformulate the Meyer Vittori sequence. Let's remember what is that. Okay, so we have two open sets on a manifold. And then we have a union of the sets, the joint union of the sets, and the intersection. And here we have two maps. Let's say like I0 and I1. And if we have that, then we have a sequence of forms, right? So we have, let's say, vector spaces generated by forms. And okay, so yeah, so you write the forms on the union, and then since when you apply the functor of forms, that's contravariant functor. So we have error into another direction. So basically, it is just a restriction of a form. If you have a form on the union, you can restrict it to U and V, and then you can restrict it to the intersection. And well, that sequence is exact, right? So in each, well, it's trivially exact, but then it gives rise to a long exact sequence of cohomology. So that's what my Vittori sequence did. And here you have the grading Q+1. Okay, that's my Vittori sequence, and now we want to do it just a bit more formally and then generalize for any covering, not necessarily covering of two sets, and study, okay, what will be the result. So first of all, let's denote by U the covering. So in our example, it will be just covering by two sets, U and V. And then let's define chains. And here we have like U that will be covering, and here it will be omega. So for now, omega is just, let's say, it's a sheaf of forms. But if you wish, for now, just notation. So here we use omega, and that will be a sum of certain vector spaces, or in general, that's abelian forms. And here you see we have two indices. So that's why it's called B complex. B complex. So since we have two variables, two indices. And in this case, we define the chains the following way. So K0, Q, will be just denoted as like zero chains in the degree Q. And that will be just Q forms on U plus Q forms on V. And like K1Q will be one chains. And here it will be the chains on the intersection. And for all other indices, it will be just 0. Okay, and so we can write it as follows. So here we have something like that. So we have 2 columns. And here we have this omega 0 of u plus omega 0 of v. Here we have omega 0 of u intersect v, omega 1 of u plus omega 1 of v, omega 1 of u intersect v, and so on. And here we have zeros. And okay, so here we have P, here we have Q. Now note that we have also 2 differentials. So first of all, we have differential D, which acts in this direction. That's just the usual differential. D, it's like from omega k of, let's say, u to omega k plus 1 of u. And so, well, the same for V and intersection, all of them. But also we have differential, which we denote by delta here. And that was just the difference, right? So you have a form on U, form on V, and you take the difference on the intersection. Like alpha beta goes to alpha minus beta. That's delta. And surely this differential, they commute, right? So you can first apply D and then take difference, it's just the same. So like I write that D composition delta is just the same as delta composition D. Okay, then it makes sense to consider the following thing. We'll consider a complex when we have summations over diagonals. Okay, like that. That will be another gradient. So here, let's say that Kn by definition will be just sum of K, P, Q, where P plus Q is N. Okay, and then we can define differential D from Kn to Kn plus 1. Well, we can define on every component. So let's say that on KPQ, we say that D is just delta plus minus 1 power P D. Okay, so how to write it? So let me just draw maybe here. Okay, so when we have P equals 0, we have just delta and D. So here we have delta, here we have D. But then when we have here P equals 1, right? So what is P? P is when we have intersection, and here we have minus D, and here we have delta. Okay. And so it means that actually when we have, we can compute D square. So what is this D square? So it will be D square plus D delta minus delta D, or maybe with another signs here, plus delta square, and this part will disappear, will be 0. Right? Exactly because of this choice, because like when we apply in one order it will be plus, another order will be minus. So where it acts, so as you see, so here when we have this K PQ, one differential acts increase one coordinate, another differential increase another coordinate, so it like their sum acts from Kn to Kn plus 1. And D square is 0. Right, so in this case, well, because D square is 0 and because delta square is also 0, so in this case that's obvious because, well, we have just 2 columns. But in general, like for other situations, it will be not so obvious, but still it will be true. And so we made a complex, graded complex, differential complex out of that situation, like that. Is it clear? Can you hear?
Yes, it's clear. Yes.
Okay, so now the claim, the theorem, is that this double complex, this C, this you beautiful D, computes the rank homology of union of U and V. The rank homology of U union V. Okay, so let's prove it. So first of all, we want to show that there are maps, like the map R from the forms on, okay, let's denote U union V by M, from the forms on M to the forms on U plus forms on V. Right, that's just by restriction. And now let's see that R is a chain map. Chain map. So it means that we have to show that it's, well, so we can compose it with differential in these complexes. So let's see how it goes. So this thing is a subset of C star of U omega. Okay, so here let's write it accurately. So we have forms on M. Here we have D. Here we have forms on M. And here we have this map R. Here we have this C star of U. Here C star of U. Here we have this big D, which is actually delta plus minus 1 P D. Okay. So let's check why it's true. Well, when we apply map R, so where we send it to the union. So we send it to the first column. Actually, so the image is here. And so it means that, so what we have to prove? So when we send a form, let's say omega here, so we want to compute dr, right? So it's first we apply R, then we apply D. So what is that? I claim that just dr. I want to have it here. Delta. Yeah, it's fine, right? Because if I have a form on the intersection on the union, then it's true that well, so let me draw it here. If I have a form, let's say a form on the union, right? So if I send it here, then by delta it's sent to 0 because it was a form on the union, right? So it means that, well, trivially I have that delta R is 0. And so because of that, I have this dr equals dr. Yeah, okay. So it means that just for the reason that the form comes from the union of U and V, this delta acts on this form as 0. And so delta just dies, and I have this property. So that's the chain map. Okay, and so it means that this map induces a map R upper star and homology. H. Well, how to denote it? So that will be the cohomology let's call it D of C star. And here we have covering. Oh my God. That's the cohomology. And with differential D. Okay, and now there are two claims. So we claim that this R upper star is surjective and injective. Injective.
Excuse me, I have a question about the diagram. About so the big D, it had I mean, when we checked that R is chain map, big D, it had a sign before the D, the usual differential.
Yeah.
So what happened to it? Because we just said that dr equals dr. Shouldn't there be a minus sign sometimes?
Yeah, you're right. So sometimes it's minus, sometimes it's plus, but yeah, but when yeah, but it uses the same map as. Okay, so correct statement is like that. So we can define this. Let's say that the map is a chain map if it commutes up to a sign. Then in this case, it defines the map in cohomology because when you construct all this like things, you consider kernels and images of maps. And actually, it doesn't matter like up to sign what happens. So the map is still well defined. Yeah, you asked the right question, and yeah, so it's frequently neglected. Yeah, so let's say here it's up to sign. Okay. Oh wait, maybe it's not up to sign. Maybe it's actually. So let's see how we define it. I think we define it. Yeah. So it's not. So here it's not up to sign. So here it's fine. So here because here in the first column it's D, and in the second column it's minus D. And since here when we come to the second column we already 0. So here actually it's just true, because here it's like. The R, it's like delta plus minus 1 power 0. Okay, because we're in the column 0.
Okay, yes.
Yeah, so it's here it's even it commutes. Okay, now let's see how to prove that R upper star is surjective and R upper star is injective. So if we prove it, we prove everything. So it's mapped from here to here. Right? Yeah. So first of all, let's see what is a cochain in this box here. So let's say we have a cochain alpha here. Alpha is a cochain here. Chain here. Well, naturally, alpha, let's say it's from the gradient Q. So it means that alpha can be presented as alpha 0 plus alpha 1, where we have alpha 0 from K0Q and alpha 1 from K1Q minus 1. Right? Because here we have just summation by diagonals. Okay, and now I claim that in this case, alpha 1 is equal to the certain delta beta. Right? That's just because of the exactness of my rotary sequence. Right? So here, if you have anything from here, it's always an image of something from the left. Right? So I can find this with this beta. And then in this case, I can say that alpha minus d beta has only this 0q component. So what I want to say that if I take any homological class from the right, from here, actually I can choose a representative which lives completely in the left column. Right? Yeah, so because when I subtract this d beta, I just keep the part alpha 1. Maybe I change the part alpha 0, but I don't care about that. Okay? Okay, so and now I can show that this map are upper star is surjective. So I choose any homological class on the right. I choose a representative which lives completely in this component q k0q, and I want to show that this class comes from the left, from the Dranko homology of M. Okay, now I have to use that it's a cochain. Okay, so let's say that's alpha. Well, maybe let's call it phi. Okay, and then I know that delta phi equals 0, and now I want to show that there exists a global form say I don't know, psi, such that R of psi equals phi. By global, I mean that it's in omega of U union V. Because phi lives in the first column, and so here that just this sums of things. Okay, so how to use the fact that delta phi is 0? As you remember, that delta phi actually it's sum of delta and d. So it means that if I took a certain form, let's say phi here, so the differential part of it goes here and part of it goes here. Okay, and if the differential is 0, it means in this case that like both images are 0. Right? So it means that in this case, if delta phi is 0, it means that d phi is 0 and delta phi is 0. And since delta phi is 0, it means that there is such a global form psi. And that's if and only if. And now this is so. So using this, we see that there is a global phi psi, and using this delta phi is 0, we also obtain that well, in this case, d psi is also 0. Well, because they're just the same form actually. And vice versa. If you have a form psi such that d psi is 0, well, because of that, we see that if we restrict it to u and v, we have that d psi still is 0, and delta of these restrictions is also 0. So it's kind of triviality. Is it fine?
I'm sorry.
Yep.
I have a question. I don't understand. You tell that alpha is a cochain from C upper star.
Yeah.
And alpha equals to alpha 0 plus alpha 1.
Yeah.
Maybe alpha is cochain from K upper star.
Well, okay, you see, so that's just different notation. So you're right. So here, you see, so that's just the same notation. So the K and C is the same, but C, it means that it's okay, what I want to say. Okay, so this complex
Maybe
is made of K. Okay, so this complex C star is this Kn plus 1, and so on. So that's what is denoted by C upper star. And it's made of summation of these forms. So maybe it's better to write Cn instead of K, right? Just to say that Cn is just sum of, not this sum, not this sum of C P U omega Q such that P plus Q is N. Maybe that's better to write like that. It completely avoid K, but then it will be too many C. So because of that, we use another letter. But well, yeah, that's it means that it's from K. So alpha is a cochain here. It means that alpha belongs, let's say, to K Q, and then it means that it has two components here and here.
Okay, thank you.
Here it's a lot of notation. Later it will be even worse. I don't know what to do about that. So here it's not that many notation. But yeah. Okay.
Okay.
So basically, what we did, we took a form from the sum on diagonal. Then we said that actually we can replace it by equivalent cochain which live on the left. Then since its differential is 0, it means that its images here and here are zeros. And then it means that it can be lifted here and to a cochain. Okay, now let's check the second claim. Let's check that it's, so we prove that it's surjective. Now let's prove that it's injective. Again, that's kind of triviality, but we have to check everything. Okay, what does it mean injective? So suppose that we have that we applied R to certain form omega, and suppose that it happened to be equivalent to 0. So it's 0 cohomology class, and happened to be d phi. Okay, so then we can say that phi can be chosen such that it's certain phi prime. Okay, but okay, so just all the same. So choose here like phi 1 plus phi 2 plus delta phi 2. So that phi 1 is from K 0 Q. Okay, just subtract this part. And then what we have that R omega is actually d phi 1, and then it's actually d of something of phi 1, and delta of phi 1 is 0. Right? So why is that? So if we had a form, let's say here on the left, let's say omega, okay, omega, we've sent it here, and then in this cohomology with complexity is 0. Then we can choose a representative which is here, which lives here, and then this form is d of somebody. So it comes from someone. Okay, maybe let me draw it here. So here we have omega, which is centered here, and here we have a phi. Then we presented phi as phi 1 plus phi 2, and such that this phi minus phi 1 is d of somebody, and so for this difference is d of some form from here. Let's call it No, so let me. So phi is here, and so the image of omega. So here it's R omega, and it's D of somebody. But then we choose phi1 here, and then this R of omega is D of phi1. But then since D of phi1 is 0, right? So in this component here, it means that phi1 can be lifted here. Okay, this D of phi1 is 0, so it can be lifted into forms on union. And then in this case, this omega is just D of phi1 in forms on union. Okay. So that's something not very well. Just some formal computation. So basically, what we did is just rewrote all these things about my rotary sequence in another way. It was like with 2 columns instead of 1. But now we say that, well, we have a B complex, and the cohomology is differential, and the cohomology of this B complex is just the same as my rotary cohomology. Okay, now we'll do it for, well, countably many or finitely many. So actually it's just the same for countably many sets in a covering. Maybe it will be more transparent. So here, what we need to have certain index set which is ordered. So G is a ordered index set, and we have the covering U as just as U alpha from G. Maybe finite, maybe infinite. Okay, and then we denote all the intersections. So, for example, U alpha B, it will be just U alpha intersect U beta, and U alpha beta gamma will be intersection of 3 of them, and so on. And so then we have the sequence of inclusions of open sets. Let's say here we have M. M is covered by disjoint union of U alpha. Now here we will have 2 maps. Here's the disjoint unions of U alpha beta, where alpha less than beta. Here it will be 3 maps. The disjoint union of U alpha beta gamma alpha less than beta less than gamma, and so on. Okay, now what are the maps here? So here you'll have delta 0, delta 1, delta 0, delta 1, delta 2, and so on. And the delta I, it will just ignore one of the indices. So it takes the U of alpha 1, alpha I, alpha K, just send it to U alpha 1, alpha I, deleted alpha K. And that's just inclusion, right? That's inclusion of open sets. Okay, and then we can do the same for forms, right? So then it induces the following map. So we have the forms on M, and it goes to the sum of the forms on the things. But now let's take the product. Right, so in the finite case, it's the same as sums, but in the infinite case, the product is not the same as sum. Right, so here we allow to have like infinite covering, and then when we have a form on M, and we cook up a form on all of these elements of covering just by restricting, it may be like infinite number of sets. So it should be product. And here also product of, and so on. Now let's define certain differential operator. So far we have just many maps here. Here 2 maps, here 3 maps, and so on. But now we can define the map just by alternating this delta. So let's say the delta of omega. That will be new delta for here. Just one delta. It will be defined as follows. So just take the alternating sum of delta I right, so here you have -1 power I omega. So what does it mean? It means that we just consider the restrictions to the there, but it's like with signs, right? So well, so we just apply here delta, where omega, for example, let's say it's omega alpha 0, alpha, let's say that here we have pi, and then this delta omega, it will be defined on, yeah, so if we have a form, for example, okay, so let's consider some example. If we have a form here, right? So it means that we have a form on every element of covering. So here we have something, and on every element of covering we have a form. So these forms may be very different. So that's like a family of forms, omega alpha. And now we want to define a family of forms on all pairwise intersections. We just take the difference. Okay, and when we have a form on pairwise intersections, we want to take just triple differences. So how to write it? So let's try to do it like that. So if you have a form omega, then we want to define what is this form omega on the sets alpha 1, alpha p plus 1. So like we have intersection, of example, of three sets. So we have omega alpha beta, omega alpha gamma, and omega beta gamma. And on the triple intersection, we want to have the sum with signs. And so here we say that it's sum of the -1 power I, and here we have omega alpha 0, alpha I, eliminated alpha p plus 1. Okay, so it's I from 0 to p plus 1. Yeah. Okay, so it means that omega alpha beta gamma, in our case, it will be omega alpha beta minus omega alpha gamma plus omega beta gamma. Yeah. And I claim that delta square is 0. Which is kind of obvious, right? Because we just, when we have a form, omega, here we have certain indices. When we apply delta 2 times, it means that we restricted it from the intersections of k sets to intersections of k plus 2 sets. But we can do it like in 2 different ways. And then when we eliminate 2 different indices in 2 different orders, we have it's up to sign, the signs will be different. Okay, so the same as for delta here. So if you have omega here, I apply delta going here, delta going here, then in this sum, all these intersections that will cancel each other. Okay, so if alpha beta here equals certain like omega alpha minus omega beta, here minus omega alpha minus omega gamma plus omega beta minus omega gamma. So this is 0. So the same is true when you do it in high dimensions. Is it clear?
Yes.
Yes.
Okay, good. So then this sequence is called the generalized Meyer-Vittori sequence. This is called the generalized Meyer-Vittori sequence. And well, the theorem that this sequence is exact. So it means that its cohomology are zeros, delta cohomology. Okay, so let's see. So what, for example, what happens in the first term here? So you have 0, it goes to a differential forms on M, and then if you have a differential form, you just restrict it to all the sets. And then when you apply delta, you just consider pairwise differences. Like on the intersections, it will be just difference like omega alpha minus omega beta. But since omega comes from a global form, all these pairwise differences are just zeros. Okay, and vice versa. Just imagine that you have a form. You have a forms given on pairwise intersections, such that all these like triple intersections, when you restrict there, the forms are zeros. So in this, okay, then I claim that such form comes as image from here. Okay, from okay, so if you have like on triple intersections, so if you have a form, right, it's here, a form omega alpha beta, so it's like a collection of forms, like form for every pairwise intersection, so that it goes to 0, then I say that it comes from here. Well, intuitively, it's very clear. So how to lift it? Just choose any lifting on one set, and then you just lift them like naturally. So, and why it's all correct? Because when you return back, like in different paths, so first you lift on alpha, then you lift on beta, then you lift on gamma. Maybe you can have some like different lift, but no, because this difference is exactly this omega alpha beta minus this one. So that's kind of explanation, but now let's have a proof. So proof as a formal statement. So for the proof, we just present a homotopy map. Okay, so let's say that we have so proof. So let's say that rho alpha is a partition of unity. For our covering. And now suppose we have omega, which is inside, let's say, product of omega, and here we have u of alpha 0, alpha pi is a picocycle. Okay, and then I want to define a p minus 1 cochain. Let's denote by tau. And let's say the following: say that tau, it should be defined on every p minus 1 intersection. So let's say alpha 0, alpha p minus 1. That will be just sum of rho alpha, omega alpha, alpha 0, alpha p minus 1. Okay, or all alpha. So what happens, I said it well, I just look at my forms. So since I have a form omega, I can look on its values on every intersection of p sets. Take the intersection there and multiply it by rho alpha. Okay, and now I claim that, okay, so what is d tau? As you remember, it's just sum of minus 1i. And here I should take alpha 0, alpha pi minus 1. And then here I should remove alpha I. Okay, and now let's remember what is this thing. On this thing is just rho alpha of this. So that's just sum of minus 1 power I rho alpha. And here I have omega alpha, alpha 0, alpha I, alpha pi. Here also let's remember about some convention. So before I wrote forms only like where the indices were increasing order, but now I can say that, for example, omega alpha beta is minus omega beta alpha. So I should say that, well, omega is such a form on, for example, on intersections, but if I want to write omega alpha beta where they ordered in the wrong order, then I should just change the sign. Okay, so here just, well, convention how to say what I mean by writing alpha here. Or if you wish, we can just write signs here, right? So we can just say that, okay, what is alpha in this, like alpha 0 and so on, and then we put it on a certain place, and then we write a sign. Then it will be fine. But well, it's not very convenient. Okay, so what we had, we had that the omega was a cocycle. So what I want to say, that every cocycle is a coboundary. So I want to show that if delta omega is 0, then omega is equal to delta somebody. And let's check it. So what is delta omega? Delta omega on this set alpha, alpha 0, alpha pi is omega alpha 0, alpha pi plus minus sum of minus 1 power I plus 1 omega alpha, alpha I, alpha pi. And we know that it's 0. And what is now delta tau on alpha 0, alpha pi? That's sum of rho alpha of what? So let's see. So where is delta tau? Yeah, that's rho alpha. And now we have the sum that's from here. Sum of minus 1 power alpha, omega alpha, omega alpha, alpha pi. And that's sum of rho alpha. And here you have this omega alpha 0, omega alpha pi, right? Because this sum is the same as here. Okay, so that's we proved it. So actually just constructed it. So instead of saying that we always can lift it, we presented it here. Okay. So it means that, so since we have this property, it means that homology of this complex are trivial. Okay. So, well, exercise. So let's say that delta Okay, so let's say K. K of omega. Delta K plus K delta is 1. So K is homotopy. Operator. Okay. And now we can say that now we have this double complex. Okay, so let's just write it in a similar way. So just write this thing that here we have so here we have omega 0 of m, omega 1 of m, omega 2 of m. And here we have k null null, k1 null, k null 1, k null 2, k1 1, k1 2, where we have this that k pq. It's also denoted as cpu omega q. It's just the product of all this q, u, alpha 0, alpha p. It's p cochains with values in the q forms. Okay, so this p stands for cochains. So here it's cochains here, the first index, and q it's kind of the coefficients, right? So it's as you know, you can consider cochains or the chains with real coefficients, with integer coefficients, with complex coefficients, or you can consider like coefficients as a q forms. So whatever it means. Okay, and so here you have p equals 0, p equals 1, and so on. Well, and then, so the horizontal maps are delta. So as we defined above, right? And the vertical maps are D. And as usual, just say that, well, now we define D as delta plus minus 1 power P of D. And okay, so what we know again is d delta square is 0, d square is 0, so d square is also 0. Okay, and well, it means that we can consider the double complex, and this c star u omega star, that's a sum of cp u omega q with delta is called the Meyer-Vittorius, the Czech-Duran chain. Czech direction. Czech-Duran complex. Well, and now the theorem is that it's this map from omega from M to this Czech-Duran complex induce isomorphism in cohomology. always. Okay, any questions before the proof? Are you here?
Yes, we're here.
Yeah, good. So, so the proof here is the same as the proof above, actually. So what happens? So we want to show that R is a chain map, but actually it's the same as before, right? Because if we have something coming from, let's say, from the left, from this column of M, then this operator delta, it's zero on it. Okay, so we don't care about, so that's a chain map. And then we need to show that this chain map induces isomorphism. So it should be surjective and injective. So how the proof was working before? We just said, okay, so we just want to somehow express any chain and then somehow like move it to another component. So here it's the same. So let's do it this way. So let's say that we have a somewhere here. Let's say that we are in this diagonal, and we have a, let's say, phi living here, and then it's equal to certain like alpha 0 plus alpha 1 plus alpha 2 plus alpha 3. Okay, then you see, so in every row here the map is exact. Right, so it means that we can kill alpha 3 and send it somehow to just to change phi to equivalent of it by applying delta of something living here. Right, so it means that we kill alpha 3 in this case. I can make it 0. Then what we know that we want to show that our upper star is surjective. So it means that we consider d phi which is 0. And if d phi is 0, it means that when you apply d, so to all these components, it will be 0, and it must be 0 here. It should go to 0. But if alpha 2 goes to 0 under delta, it means that I can find certain element here, such that alpha 2 is an image of it. So I can add d of this element 2, means that I kill alpha 2, and now I change alpha 1, and so on. That I do just because in every row is exact, because it's homology are trivial. So it means that actually I can express any class phi to certain class alpha 0, which lives just in K this 0 view. And again, since delta of this class is 0, it can be lifted here to the forms on M. And since d of it is also 0, it leads to a cochain. It leads to exact form. Okay, and it's the same. That's about injectivity. So if you have certain form which goes to 0, so it means that you apply R to certain omega, and that's equal to d of somebody, d of phi. So here it was omega, you apply R omega, and it's D of somebody living here. Then again, it means that, okay, so if it's 0, it means that the last component here is 0. So your class comes from somebody from here. And then we can just twist this class by adding this part, by changing this element. So we can assure that this element is also 0 by twisting it, by adding something from here. And again, since in this component it's 0, because it's well, it's r omega is 0 here. We can change it in this way until we just present that r omega is delta of some form living here. And then phi is left here. Can be lifted to the left. So that's just the same proof as for the pair. Well, any questions?
No questions.
Okay, good. And then, so we proved that this B complex computes the cohomology of M. That's good. Why it's also good? Because it allows us to do the following. So let's look at the picture again. So here you have certain groups, K0, 0, K1, 0, and so on. And here we have this omega 0 of M, omega 1 of M, omega 2 of M, and so on. So indeed, it's natural to add something in the row below of it. So let's call it C0 U R. Okay, because here we have K null null. What is that? It's just product of omega 0 of U alpha. Right, so it was just constant functions on the covering of U alpha, and we can just look at the well, this thing, and here it's will be just C1 of U R and so on. So what happens? We just added by exactness. So what is that? So we add constants, right? Because omega null is just functions, right? And so what is the differential? The differential is the differential. So it means that this C null is just locally constant functions. So here it's locally constant functions. And well, these are locally constant functions on intersections, locally constant on U alpha beta and so on. So the first row, maybe let me find this picture with forms. Here on the first picture. So here I should add here locally constant functions on U and V, and here locally constant functions on the intersection. So locally constant functions on U and V are just R squared, and locally constant functions on intersections are just R. Okay, and then, well, in this complex, we also have differential. So just the same as before. So here, it's also the same delta, just taking the differences. Right? So if you have a locally constant function on like two sets U and V, you subtract them and you have a constant function on the intersection of U and V. And so it means also that this complex C0 U R delta C1 U R and so on, it's a differential complex. And that's called, well, the cohomology of this complex are called Czech cohomology. The Czech cohomology of this covering U, of the covering U. So if you have a covering, you just form a complex where each component that's of constant functions on intersections. That's sum of such functions. We define the differential, and then, okay, so it means that we can look at this table like in two ways. So before we look at like from the left, and now we can look at from the bottom. Right, so, and it means that if these columns are exact, so if the columns of well, this table are exact, then the cohomology of the complex, also the cohomology of as a Czech cohomology. Right, so it means that this cohomology of this UR, the Czech cohomology, they denoted as HUR. They're isomorphic to the usual Durham cohomology. Durham cohomology. Durham, like that. Durham cohomology of M and R. And so when it happens, so it means that if the columns are exact, it means that all these products of cohomologies of U alpha P are zeros. So that happens when all finite non-empty intersections are contractible. So if all finite intersections of U alpha are contractible, then these cohomologies are zeros, and so all the columns also exact, right? Because each column, that's exactly what happens in the intersections. So if all the intersections are like contractible, so all the cohomologies are zero. So all the cohomologies are concentrated in the zero dimension, and that's exactly what you write here. So if you wish, this chains in the Czech complex are zeros cohomologies of the columns of our table. And if all the other are trivial, so it means that the cohomology of this complex below, that's the cohomology of all this B complex. So that's the same argument as about cohomologies of the column here. Okay, and now so why it's all good? Because this thinks that's about combinatorics of the covering, right? So we know that if you want to compute the Durham cohomology, we have to consider certain forms, exact forms, closed forms, and so on. But now we reduce the question to the following. So let's cover the manifold by maps, such that all the intersections are contractible. And now, if you know how all these maps intersect each other, then we know the Czech complex, which computes the same cohomology. So in this way, for example, you can show that the Durham cohomology are the same as simplicial cohomology, right? Because if you have some simplicial representation of your manifold like that, right, then that's how you choose the covering. Just as a covering, choose the small neighborhood of every cell. Okay, so this one cell, another cell, another cell, another cell. And well, and actually the intersections of these elements of the covering, they encode exactly the simplicial structure of the complex. Because if you have two simplices which intersect, which share a common face, it means exactly that this corresponding coverings, the intersection is not empty. And so let me just say it. So the Czech complex is isomorphic to a simplicial complex, the complex of simplicial, well, complex for simplicial homology. Any questions here? Also from here, for example, it follows, so the Czech cohomology are the same for all good coverings.
I'm sorry, you said that all of the finite intersections must be contractible.
No, not must be. I mean,
Yes.
so if all the finite intersections are contractible, then that's true. So then the homology of any column will be concentrated in dimension 0. But you can ask, okay, so let's say that the 0 cohomology of any intersection, okay, let me say it here. So here, so what we want is that we want that HK for any intersection is not 0 only if Q is 0. So that's what we want. So it's okay. So if are not contractible, but the cohomology of well, this thing of the column are zeros.
And then the Czech cohomology will be just the usual cohomology.
And then, well, so it depends on what you mean by usual. So if you have simplicial, so if
Isomorphic to simplicial or singular.
yeah, so to simplicial, to singular, it's well another thing. So so to simplicial, because so if you have manifold, you choose a simplicial representation of it. So it means that you just find the collection of simplices which cover it inside the intersection of any two simplices is again a simplex. Then you say that, well, now I take small neighborhood of all the simplices, and then the intersection of small neighbors will be the small neighbor of intersection. And then since the small neighborhood of any simplex is contractible, then it's true. And then you just see in our definition, the Czech complex, what we see. So in all the terms that are just constant functions on intersections of our covering. But if all the intersections are in bijection with simplices, then it means that it's just the same as constant functions on simplices. But what is the constant functions on simplices? That's exactly a simplicial chain, right? Because when you consider a sum of simplices with coefficients, you just treat every coefficient as a function with this value on this simplex. I think that's simplicial cohomology, right? Because for cohomology you can consider like yeah, I think it's for Yeah, it's simplicial cohomology. Let's see. No, I know it's a simplicial homology, right? Because if we have a function like constant for one phase, constant for another phase, then we have this phase with a constant C1 minus C2. That's a map in homology, right? And when you consider chains. Yeah. Okay, more questions? Maybe consider an example with a circle. So well, we have a circle that's covered by 3 open sets. And then we have C null of U R that just functions on each of them. So it will be just R plus R plus R, 3 constants, right? So it's like omega 0 here, omega 1 here, omega 2 here. That's a Czech complex. Then we have C1 of U R, that's on the intersections. That's also R plus R plus R. So here you have this omega 0, 1, omega 0, 2, and omega 1, 2, which obtain just as difference. Okay, maybe not omega, let's say alpha. Okay, and finally, so all the intersections of 3 sets are empty, so it's just 0. So it means we have this delta from C0 to C1. Well, if you have, let's say this omega 0, omega 1, omega 2, you just consider this omega 0 minus omega 1, omega, well, it was omega 1 minus omega 2, omega 0 minus omega 2, and omega 0 minus omega 1. So that's the map. And so the kernel, that just constant functions on the circle. So H0 of S1 is R. Okay, and the image of delta is R2 clearly inside C1. So H1 of S1 is also this C1. 2 is also R1. Okay, so we managed to compute cohomology of a circle. So the same about S2, for example, for S2. So we can cover S2 by 4 sets, right? So you need like 1 set, second set. Then and on other part of the sphere, you also have a third, and like on another thing. And here fourth here, and on the other side. And so here you have like 4 sets. You have all pairwise intersections, all triple intersections, but no intersection of 4 sets. And so this corresponds exactly to the like complex like that. So here you have 1, 2, 3, 4, but without the face inside, like the surface of a tetrahedron. Okay, what else can we study today? Okay, I think that's all for today. So in the next time, so what we can do the next time? So let's say that next time we will study shifts. because it's almost what we did here. So next time shifts and shift cohomology. So next time shifts and sphere bundles and error class. So any questions today?
Is there something like Czech homology, like
No, as far as I know,
analogous to?
no. Well, you can define something just dual object, but no.
And is there some like geometric formation of what Czech cohomology are? Like
Yeah, it's just combinatorics of a good covering. So if you manage to cover your, I don't know, your manifold by disk, like geodetic disk, then this Czech homology encodes you everything about homology of your manifold, just because you know how the disk intersect. So they contain all the information. But why it's maybe better sometimes than the simplicial cohomology? Imagine that you have a space which is not a manifold. I don't know, some space in dynamical systems with strange topology, whatever. And you can define simplicial cohomology or like singular cohomology, but they may be strange because like for simplicial cohomology, you need simplicial structure, but maybe there is no simplicial structure. For singular homology, you consider all the maps from intervals, from points, and so on. It also may be strange. But this Czech homology, you said, well, we just cover your space with relatively good sets, and Czech homology are defined. So, for example, it's not necessarily to cover your space by contractible sets such as the intersection are also contractible. You just cover something. This is say that for such coverings, well, you can compute certain cohomologies.
And it will be like homotopically invariant because from the definition, it's I think it's not very obvious.
Oh, you see, so it's all they all coincide in for the case of manifolds. So if you have manifold,
but in the case of any topological space, this is homotopy invariant.
It's not clear because this is so in principle Czech homology they depend on covering.
Yes.
So if you cover a space by contractible sets, then I think it should be homotopy invariant. But well, I'm not sure. So I never thinking. I was never thinking about that. Maybe it's not true. It should be true, right? No. I don't know. So I should check. At least it's not obvious immediately.
Yeah.
So the advantage of singular cohomology, because singular cohomology they immediately homotopy invariant. That's because people like to define them, right? So you define singular cohomology, you study homotopy, it's all fine. When you say that, okay, let's study simplicial homology, then it's not so easy to prove that it's homotopy invariant. So it's some pain. And again, so it's only in the space of simplicial complexes. So you need to show that any homotopy is homotopic to simplicial homotopy and so on and so on. So just immediately you have a lot of problems. But simplicial homology is much easier to compute. So the same with Czech homology. It's easy to define just for any space, and sometimes it's easy to compute, but I believe that there should be some problems. For example, maybe like in principle, they're not homotopic invariant. I don't know. So one should check in the internet, in any book.
Okay.
There are also versions of homology, some kind of Alexander homology or something like that. So when people consider all the maps of like endpoints to the space, and there's certain topology on the space of all the maps of endpoints and so on. They are kind of close to the Chekhov homology, but again, I don't know. Like, so for good spaces, all this homology theories are the same, but for bad spaces, they may be different. Yeah, let's stop recording.